Okay, this is the third instalment of, and final instalment of Edexcel's International S1 paper of January 16. The first part is a relatively standard normal distribution question. Well, it's all normal distribution, but the first part is definitely pretty standard. We've been given the mean and the standard deviation, so we're not really too much of a great mystery there. We're given the mean. We're given the standard deviation, so we write it like that. The variance is 10 squared. I do think it's a good idea to draw lots of diagrams for your normal distribution questions. This one's just going to show my original X distribution, not the Z one, which we change it to in a moment, but the X one. So the mean is 22, and what we're looking for is the probability of it being less than 18. Okay, I think that makes it clear that we're looking for some value of less than 0.5, because quite a lot less than 0.5 to be honest, but because we can see that the red bit there is less than half under the graph, and the graph should have a total area of 1 underneath. So that should ensure that we don't make some howling mistake here, because we're expecting an answer less than 0.5 immediately without really doing much at all. Okay, so always when we're working with normal distribution, we're transforming this to the Z distribution, where Z is X take away the mean divided by the standard deviation. Okay, so we're being asked for the probability of X being less than 18, which is exactly the same as the probability that Z is less than 18 take away the mean divided by the standard deviation, which is 10. So that gives me that probability that Z is less than minus 0.4. Now here, I'm going to draw the Z distribution here. And this is now Z with minus 0.4 here. Numbers to the left of the mean value here are always negative with the Z distribution because we've got 0 in the middle. And we can see by symmetry that it's exactly the same as the area I'm just shading now on the right. So that's the same as the probability that Z is greater than 0.4. Okay, well, now the tables, let's maybe shade this in a different colour. The tables are going to give us values this side here, all of it. That's what, if we look at 0.4 on the table, that's what it's going to give us. Okay, so what we want to do is do 1 minus the number that we read in the tables. If we want to write that formally, and it really isn't necessary you write all the formal maths that I'm doing, but I'm going to do it just to make it look a bit fancy, and if you like doing that type of thing, fine. But it's really not necessary to go into so much detail, but sometimes I find it easier as a teacher and a tutor just to write it formally, so that if someone watches me, they're not saying that I'm some kind of fraud, but really it's not necessary to actually do it this formally. So we've got the probability that Z is less than 0.4. And some people then even go one stage further and talk about the psi value, which is the same thing here. That's what the psi value is. It's the probability that the psi of X is the probability that X is less than X. You won't see me doing that, going that far. I really don't see the need for that. As kind of elegant as it all looks and all the rest of it. Anyway, if we look at this now, if we look at 0.4 in the tables, we've got these tables here. We look at 0.4 and we get the value 6.6554. So that's 1 minus 0.6554, which comes to 0.35 446. No, what am I talking about? 0.3. Yes, it was right. 0.3446. Okay, that's fine. So that's that question done. Now, that was just to reiterate. I've probably written more than I needed to, and it'd probably be okay to skip all of this out. And remember what I said at the beginning. I could see it here. I can see it here. I'm expecting a number less than 0.5, so I can almost, you know, I've tried to explain why this is the case here, but I can almost ignore the negative sign here, read the 0.4 and do 1 minus, because I know that the answer I'm expecting is less than 0.5. And yeah, so that would skip out the steps I've written there. Okay. I'm not saying you should do or shouldn't do, but it is acceptable. Okay. Now part B. Right, let's have a look at part B. It says the local beekeeper always club awards a certificate to every hive that produces more than 39 kilograms of honey in a season, and a medal to every hive that produces more than 50 kilograms in a season. Okay, remember the mean of this thing was 22 kilograms. Okay, it's got quite a high standard deviation in this, so you know you can. It's not surprising that you might have some that are bigger than 39 or even 50. So this is another conditional probability situation, which looks kind of similar, as you'll see in a moment. For those of you who've looked at the other video on question, I think it was 3 or might have been 4. You've got a situation where we need to work out. We need to work out the probability that x is greater than 39. We also need to work out the probability that x is greater than 50. And then we can deal with the probability bit after that. So let's talk about that first of all. So we've got these two values here, 39 and 50. Obviously 50 being the harder one to achieve, but both of them, one of them getting one of them a certificate and the other one a greater accolade of getting a medal as well. So let's work out the probability of x being greater than 39. So that's equal to the probability that z is greater than 39, take away the mean, which is equal to 22 over the standard deviation. So that equals to probability that z is greater than 1.7. Now again, we could draw this on a diagram, either the original X distribution or the Z distribution here. We know that we're looking for a number less than 0.5, so we're going to do 1 minus. So it's 0.9554. So it's 1 minus 0.9554. And that gives us 0.00446. Right, we then work out the probability that x is greater than 50. Same side of the distribution here, so we've got the probability that z is greater than 50, take away 22 over 10. The probability, which is equal to, so I've printed this off from the original and I'm going around the paper, so it's looking a bit strange, but never mind. So we've got probability that z is greater than 50 minus 22, that's z is greater than 2.8. Again, we're doing 1 minus for the same reasons as we were before. So 2.8 is in the tables, we're getting 9974. So it's 1 minus 0.9974 because we're expecting a number less than 0.5. So that's equal to 0.00226. Okay, so let's bring all this together. Okay, so just to recap now, we've got two probabilities here. I'm going to try and explain this carefully. We've got probability that x is greater than 39. Obviously this is a very exaggerated diagram because these are both very small numbers, but it's the only way I can try and get this idea across. So that's 0.0446 for that area. We've then got an even tighter, an even more extremely good performance, because remember to the right in this context is good, of 0.0026 for if the figure is more than 50. Okay, what we're being asked for, to go back to the original question, is given that one of Rosie's beehives is awarded a certificate, so in other words we know that it's more than 39, find the probability that they get a medal which is greater than 50. So basically we're being asked for, find the probability that x is greater than 50 given that we know that x is greater than 39. Now you might intuitively have a feel for this, or you might not. So I'm going to try and, some of you may think, well, intuitively, and that's absolutely fine. You might think, well, isn't that just the proportion of the numbers, one number divided by the other number? And you would be absolutely right. We're basically going to divide the smaller number there by the bigger number. Okay, so you might feel that because basically we know that one of this is going to happen, so we divide the smaller one by the bigger one, and you can do that in all of these situations. But some of you may not be happy with that. But if you wanted to just write down that now, write down 0.0026 over 0.00446, and just write that as your offer, because you kind of intuitively can see that, because if you know one of these is going to happen, then the other one, it's basically becomes a whole, sometimes called a reduced sample space. This becomes one of these is certain happens, so it's a basic ratio of one to the other. But I have certainly students that I tutor and teach that we're not like that, so I'm going to try and do it more formally, but feel free to just write down the answer when you see it. Basically, we use the normal rule of conditional probability, says this, or the multiplication rule if you like, says something like this. Probability that, I don't know why that's just suddenly appeared, I think it's not really working on a tech level today. Probability that A conditional on B is equal to the probability of A and B divided by the probability of B. That's out the rule. So you might want to think, well, how does that work in this context? And if you're that person, and there are many people like that, then I'm just going to try and explain why that's the case. Right. Okay, so let's rub that out now, because I'm just trying to, that basically means the probability that x is greater than 50 intersection, now this is a bit over the top as you'll see in a minute, and it's very similar to a question that we had in this context, in this particular aspect, earlier in this paper, so, which is a bit unusual that they've done the same kind of idea in two different questions, but they have. Basically, it's that, but really this is a little bit over the top, because if this is true, sorry that's the wrong way around, but you go, if this is true, then this is definitely true, because this is a tighter condition. It's again a similar situation where we've got one event inside the other. So really, I can rub this bit off here because they're basically the same. So that's where my numbers come from that I've mentioned before. So that's 0.026 divided by 0.0446, and that gives me 0.0446 0.0582. 583 to three significant figures. Okay, so that was, I say, it felt a bit similar to a question we've already seen, but kind of conditional probability where one event lies inside the other. Okay, right, there's still another bit. I thought I was going to get this done quickly, but apparently not. Okay, question C is all about another thing going on here, and it's actually a pretty common type of question. I'm just going to make a bit of room for it so I can, I'm going to get rid of part A, and so we've got enough room for part C, and then we can have a look at the question. Okay, so this is a relatively standard work. I sometimes call these working backward questions because we're given probabilities and we're working out stuff from that. We're given some information. So some also keeps bees. The amount of honey in kilograms produced by a hive that sends bees in is modelled by a normal distribution with mean mu and unknown standard deviation. Also, the probability hives produces less than 28 kilograms of bees is 0.813. Now, diagram, definitely start with 0.813. Don't know why it keeps flickering at the moment, but I'm going to carry on. 0.813, typically I've written it in the wrong place, getting distracted by certain funny things happening here. So there we go, 0.8413 is that area. Now I knew it's got to be this side of the mean. So the mean is going to, the most basic thing I should know here is that the mean is less than 28 because I've got a probability of more than 0.5. You really ought to know your normal distribution, 0.5 one side, 0.5 the other side. Okay, so that's going to help us a lot because we're going to have to do the Z transformation. And work with that. It says only 20% of some species produce less than 18 kilograms in a season. Right, so that also means, perhaps if I write two sides of this, you can write it almost in two columns. So only 20% produce less than 18. So we've got 20% here. Okay, 0.2. And that number is 18. So on the most basic level, we know that our mean is somewhere between 18 and 28. Okay, if we don't get an answer like that, then we really know that we're in trouble. Okay, so let's write this out. Probability that x, and we'll do them one by one, x is less than 28 is equal to 0.8413. So that means that the probability that now we can do our transformation. Z, take away the mean. Oh, sorry, no, I'm talking a bit strangely. Z is less than 28, take away the mean divided by the standard deviation, and the standard deviation is also unknown, is equal to 0.8413. Right, now what is very important that we see here is when we move to the Z value, we want a positive Z value because we're to the right. We've got a 0 here, so we want to find the appropriate Z value which represents 0.8413. Now these numbers we can look in here. We're looking for the numbers backwards. Now when you're given the numbers to 4 significant figures like that, the chances are it's going to be bang on something. 0.8413 is 1. So our Z value is 1. So that gives us that 28 minus mu over sigma equals to 1. Really don't know why it's flickering like that. Then let's do the next part. Probability that x is less than 18 is equal to 0.2. That means the probability that z is less than 18 take away the mean over the standard deviation is 0.2. Now, as we've said before, we're expecting a negative z value here because we've got a 0 here, so we're expecting negative with this 0.2. Right, so the thing is, we might say it's the same as the positive z value if we've got 0.2 here. So we're looking for so we're basically looking for perhaps 0.8 here. But when we look at 0.8, it doesn't come exactly in the tables. We could try interpolating or something and say it's 0.84 or something. But normally when we've got something, a number bang on, there's another set of tables, and they're these ones, and it's kind of confusing because they're the other way around. They represent the numbers on the right hand side, and they've reversed the P and the Z. But we can see the appropriate number, and I often say to students, do work out the number from these tables first to get an idea what it should be. Remember, it was 0.2, so we did 1 minus, and we're looking for 0.8 in these tables, so we're looking somewhere around here. Okay, but in these tables, because it's from this side that they're reading it, we're actually looking for 0.2, and we can see the number more accurate at 0.8416. So there we have, if I can find where the question was again, in the midst of all this stuff, the probability that, so that gives us that Z, this number here, reading it again, I'm going to have to go back again, 0.8416. It is quite confusing, particularly when these numbers are quite similar. Okay, this is a Z value. The key's in the, I suppose, don't want to sound sarcastic, but the key is in the column it's in. It's the Z value, whereas in this case, the Z values are on the left-hand side. Anyway, we've got 0.8416 there. Now, that means that 18 take away the mean divided by the standard deviation, now be careful, is minus 0.8416. So that gives us a simultaneous equation, okay, which I'm about to solve. So multiplying by sigma for this one and rearranging, we're going to get mu is equal to 28 minus sigma. And multiplying by sigma and then multiplying out from that one, we're going to get mu is equal to 18 plus 0.8416 sigma. So if we equate these two, so we're solving simultaneously now, so solving, we get 28 minus sigma is equal to 18 plus 0.8416 sigma. So that gives me 1.8416 sigma is equal to 10. So standard deviation is 10 divided by that, which gives me 5.43. Right, now, you might feel like we spent 25 minutes on one question. Obviously, I've been waffling on a bit and had technical issues too, so it would be quicker in the exam. But there is only 6 questions on the paper, but when you've done a lot of work, it's easy to forget to do the final bit. You've got to work out mu as well. So mu is equal to 28 minus 5.43. So mu is equal to 22.57. That's done, finally. Okay, I feel like I need a break, but we're going to do question 6 now. Okay, so last question. It's mean standard deviation, but it's got a bit of a twist to it. I often don't use these formulas when we're calculating the mean and standard deviations. If we look at the formula in the formula book, get it somewhere. It should be somewhere. I'll just pull them up. Oh, but wait a minute. There are no formulas in the formula book for the mean and standard deviation. All your correlation regression stuff is there, but not mean and standard deviation. The mean should be no problem. The standard deviation is this number divided by the number of numbers there are. So the mean is equal to sigma x over n. So that's 8360 divided by 10, so that's 836. Okay, that's not too bad. The standard deviation is equal to the square root of sigma x minus x bar squared over n. Right, now some of you might be thinking that's not the formula I normally use. I don't normally encourage use of this formula when you're given a set of data because it involves taking the mean away from the number of numbers all the time. However, this is what we're given now. The formula we normally use, I would normally encourage students to use, is more like this. That's the formula to use, but suddenly they've changed it. So they haven't given us sigma x squared and mu squared and n. They expect us to know this as well, which is actually more intuitive because what the standard deviation is the measure of spread, and what we're doing is we're basically finding the average deviation from the mean, which would give us a measure of spread. And this is also why we square root it, because we're squaring it here, so we square root it to kind of undo that effect. So basically we're using this formula. So it's not going to be very difficult to work it out. We've got sigma is equal to the square root of 63840 divided by the standard deviation, which is 10. So that equals to the square root of 6384, which is equal to 79.89993. Let's give 3 significant figures, 79.9 to 3 significant figures. Okay. Right, now let's carry on with this. So we've got B. Given that the median is 815, describe the skewness and given a reason as well. So we can't just take a guess. There's 2 marks for it anyway. Well, the answer is that if we've got the mean greater, the test is whether the mean is greater than the median here. Well, we've got the median is 79.9. But the median weight of this is 815 grams, but the median of here is 836 grams. So in this case, we've got 836 is clearly more than 815. So that means the mean is greater than the median. So if we were to do a graph for it, that's a test for skewness, whether the median is greater than the median. And in this case, we're not talking about the mode, but the mode we expect would be greater still, because it's more affected by outliers and whatever. The graph for this, with the mean being greater than the median, would be something like this. And the median being here, and the mean being here. And that's positive skew. Because what's happening is the mean is being dragged up by larger values of the tail there. So that's called positive skew. Therefore, positive skew. Right, now, it says 2 more rabbits, part C. 2 more rabbits weighing 776 and 896 are added to make a group of 12 rabbits. State, given a reason, how this inclusion of would affect the mean. Well, we've got the mean is 836. What we notice is that both of these are equal distance from the mean. So in other words, we've got 836 take away 776. Okay, is equal to 60. Should have been able to work that out really. So, and then also the larger one, 896, take away 836, is also equal to 60. So the mean is unaffected, is the same. Since, you know, one of them's positive and the other one's negative. Okay, 60, but this is 60 below, and this is 60 above. So the mean is unaffected, clearly. Okay, in the final run now, but there's only 2 marks here, but it's tricky, and it's a very mean 2 marks for the amount of work we've got to do. Right, it says, by considering the change in this, state what the effect the inclusion of these 2 rabbits would have on the standard deviation. Well, we can work out the mean, as we know, is still 836. Okay, and the standard deviation we want to work out, but we know therefore that the sigma of x minus x squared for all the other values will still be the same. So we'll still have the 63840 for the first 10 rabbits because the mean is still the same. But we've got these 2 extra values onto that, which is x minus the mean squared. So that's our 776 take away 836 squared for the smaller one, plus the other one, 896 take away 836. Well, I should have really written 60. We already knew that they were deviated 60 from the mean, so forgive me if you think I'm making an absolute meal of this. That's 60 and that's 60. But anyway, we're increasing this value by that amount. So that comes to 63840 plus 2 times 60 squared. What I'm putting on my calculator. So that's 71040. Okay, so the new standard deviation is going to be equal to 71040 divided by 12, the square root of that. Okay, and that equals 76.9. So that means we do need to, because it didn't actually ask for the standard deviation, so we must answer the question, what effect it would have. So the effect is it would reduce the standard deviation. So standard deviation is reduced. Because basically the new numbers are closer than the average they were on average for the numbers before. Standard deviation is reduced. Okay, so that is it. I mean, I suppose we didn't really need to, we didn't really need to square root all this. We could have compared this number here with this number here without square rooting and working it out, but whatever, we've done it. And we've got there. It's been 35 minutes. The video before took 30 minutes. I think in total it's taken an hour and a half for this paper, but I have been chatting on. But it is quite a challenge, S1 at times, and not to be taken lightly. I hope you enjoyed it. Okay, bye.